This video will look at two more sorting algorithms. So, as we saw in the previous video, sorting algorithms unsurprisingly are used to sort data in different ways, often to go from highest to lowest or from lowest to highest. And there are some standard sorting algorithms that have been developed, and they've each got their own benefits and disadvantages. What we're going to do is look at the merge sort algorithm and also the quicksort algorithm in this presentation. So let's begin with the merge sort. So with the merge sort, we will start off with a set of data that is not in order. And what the merge sort will do is it will first of all repeatedly split the array into subarrays until it can't be split up any further. So it's all split up into individual items. Now the second half of the merge sort algorithm will then be to join these items up to form larger and larger arrays where the data is in order. So it will begin by looking at each pair of individual items, compare the items and order them, putting them into a new subarray of twice the size. So here you can see that the 6 and the 2 are compared and they are put into a subarray, into a new array where they are in the order of 2 and 6. The 1 and the 8 are then compared and they are paired together in their own array in order, and that happens for all the items that have been split up into individual values. Once that has happened, the algorithm will then look at pairs of pairs. So it will look at the pair or the array which contains the 2 and the 6, the array that contains in this case the 1 and the 8, and then it will start to form an array of 4 items in size in order. So the first item in the first of the arrays will be compared with the first item in the second of the arrays. The 2 and the 1 will be compared. The 1 is smallest, so that will be copied into the new array in the first position. Then the 2 will be compared with the 8, and the 2 is the smaller of those two values, so that will then be copied into the new array in position 2. Then the 6 and the 8 will be compared, and the 6 will be brought down, and the 8 obviously is left, so that will be brought down and take the last place in that array. That will then repeat for the next pair of pairs. So you can see here that the 3 and the 4 are compared, the 3 is smaller, so that comes down. The 5 and the 4 is compared, the 4 comes down. The 5 and the 7 are compared, the 5 comes down, and the 7 then comes down. So we've now got our new array, which has been formed by the pairs of pairs, but you can see that they're now in order. That then continues again. This time we are comparing 2 arrays, each with 4 items in them. So the first of each of those items, first of each of the arrays will be compared, and the smaller one will be copied into a new array. And this continues just like it did before, to form an array which in this case was the size of the original array that the merge sort started working on, but you can see now that all of the items have been ordered. So this is the merge sort algorithm. So it repeatedly splits an array up into subarrays until each of those subarrays contains just one item. Then for each pair of subarrays, the values in them are compared, and then they are reordered inside a brand new array. This is repeated over and over again so that the subarrays are doubled in size, being reformed back to the original, but this time with the items inside being ordered. And obviously it stops when we can't carry on increasing size, because we've eventually got one single array with all of the items now in an ordered form. Okay, so let's have a look at the quicksort. So the quicksort again starts with a set of data to be ordered. Now, this works very differently in certain respects from the merge sort, because with this one we are going to be using something called a pivot, and in the best cases the pivot will be fairly central to the array. Once we've found a pivot, we will have a left pointer which will point to the first item, and we'll have a right pointer which will point to the last item, as you can see there. Then what happens is that the item that is at the left pointer, so in this case the number 1, is compared with the item at the pivot, which is a 3. Because 1 is less than 3, we know it is the correct side of the pivot, so therefore we just we leave the 1 where it is and we advance the left pointer on 1 so we can look at the next item in the array. So the 4 is the next item, that's compared with the pivot. Now in this case the 4 is bigger than the pivot, so what we do is we stop advancing that left pointer. The left pointer fixes in position, and now the attention turns to the right pointer. So focusing on the right pointer, which is at value 6, that is compared with the 3. Now the 6 is greater than the 3, so it's also the correct side of the pivot. So the left pointer moves down 1 to the next item. So here you can see that it is pointing at a 2. The 2 is compared with the pivot. 2 is smaller than the pivot, it's the wrong side of the pivot. So we therefore stop moving that right pointer. So we've now got our left pointer at 4, and we've got the right pointer at 2. Now what happens is we obviously want the 2, which is less than the 3, to be on the left hand side, and we want the 4, which is greater than 3, to be on the right hand side. So the items at each of those pointers swap positions. So you can see here now that the left pointer is now pointing at a 2, and the right pointer is now pointing at the 4. The 4 is the correct side of the pivot, the 2 is the correct side of the pivot also. So the items have swapped, and what we can now do is we can move the left pointer on 1 to the value of 5. Now 5 is greater than 3, so we stop moving our left pointer and attention turns to the right pointer. That is at a 4. Now the 4 is greater than the 3, so that's absolutely fine, that's at the correct position. So what happens is that the right pointer moves down 1 to the 3. Now the pointer is now at the pivot. So what we then do is we swap these two items. So the item that was at the right pointer and the item that was at the left pointer, they swap position, and you can now see that we've got an array where we have already worked our way from left and right sides to the center, and finally swapped at the pivot. The items in this array are not ordered. Okay, they're still not ordered. So what the quicksort algorithm will do, because it uses the principles of divide and conquer, it will now split this array into two smaller arrays, and it will repeat the process again. So it will pick a pivot, it will pick a left pointer and a right pointer for each of these sub-arrays, and it will repeat the process that we've just seen on each of these sub-arrays to try and order them. So the entire process is repeated on each sub-array until the sub-arrays are ordered. They're then joined back together to reform the original array, which will now be sorted. So again, to explain how it works, the algorithm will choose a value to be the pivot, and in the best case it should really be very central to that array. It then takes two variables to point left and to point right, excluding the pivot, so it should really be on the left hand side, the left pointer, and on the right hand side of the array be the right pointer. That's what step 3 and 4 are doing. And then step 5, while value at left is less than the pivot, keep moving it right, and whilst the value at the right pointer is greater than the pivot, keep moving that pointer left. And if both steps 5 and 6 do not match, then swap the left and right over. If the left pointer is greater than or equal to the right, then we know that we've met, those pointers have met. Then at that point the algorithm will split the array up into smaller subarrays and repeat the process. So both merge sort and quicksort, they use divide and conquer. They repeatedly halve the dataset while attempting to order it. Now remember, if the size of the dataset is doubled in length, it only requires one more step during the halving operation or the doubling operation. And because of that, they're really efficient. They're logarithmic in nature. So, you know, doubling the size only requires one more step. That's really efficient. If you scale up the algorithm that you have to work through, if you're doubling it, making it twice as big, and you only have to do one more operation, then that's great. That's really efficient. So as the dataset grows, the time taken to sort the data does not increase at the same rate, and that's really important to recognize with any algorithm that uses this divide and conquer method. But it's not as straightforward as that. Let's have a look at the big O notation for merge sort and quicksort and really try and understand why it is what it is. So let's have a look at the merge sort. Now in the worst case scenario, the merge sort has a big O notation of n times log n, where n is the size of the data set. So if you think about that, n times log n, the n part, well, that's linear in nature. As the data set grows, the time it will take to sort will grow at the same rate. Log n is logarithmic. That means that for increasing sizes of data, the time it takes to operate on that data set doesn't increase at the same rate. In fact, its increase in time does not, it increases progressively slower. So in the worst case, the list will be reverse sorted. Biggest first, smallest at the end. And if you think about the merge sort, there's two parts to it. There's the part where it halves and doubles data sets in size. And then there's the other half where it's comparing each item and ordering them. So the halving and the doubling steps of the merge sort, they are logarithmic in nature. Okay, so remember, for a data set of double the size, only one more halving or doubling operation is required. However, the merge sort also needs to work through the sets of data after each time it's sort of doubled in size. It still needs to compare the items and order them. And because it's going to compare each of the values in turn and order them, that part of the algorithm is linear in nature. So combining those two qualities, the big O for the merge sort is O n times log n. So you've got the linear part where it's comparing each of the items and the logarithmic part where you're halving and doubling. So putting that together, in the worst case, the merge sort big O is O n log n. Now for the quicksort algorithm, the big O notation most of the time on an average situation would be O n log n. Now when I say sort of most of the time, that's if the pivot is central most of the time. Every time the array splits, if the pivot is central on that next step of ordering the data, then it usually is fairly efficient and comes out at O n log n. But in the worst case, the quicksort is actually O n squared. So let's have a look to see why it's O n log n in the average case. So like the merge sort, the quicksort uses this divide and conquer principle to work on repeatedly smaller data sets by halving, doubling. So if the pivot is central in each case, this is logarithmic in nature. Every time you halve the data set, you're splitting it into two, that's logarithmic. And during each ordering step of the algorithm, the operations carried out are in direct proportion to the size of the data set, so they're linear in nature. So what we mean by that is every time you're actually working through or passing through an array, comparing the items at each of the pointers, you're working through each item in turn, so that's linear. that is in direct proportion to the size of the data set. So combining those two qualities, the big O for the quicksort, if the pivot is always central, it's O(n) log n, or just O(n) times log n, or just O(n) log n. However, the pivot may not always be central, and so in the worst case, the benefits of the divide and conquer principle may be negated, leaving the algorithm with a big O of O(n) squared. So it's always important to be mindful of that if you ever have an exam question on the big O complexity for a quicksort. Most of the time it uses divide and conquer really efficiently because the pivot's central, so it's O(n) log n. But if the pivot isn't central, in the worst case, the big O comes out much less efficiently as n squared.